The last topic for us to cover in this section is the denseness of rational numbers. Basically, that says that between any two rational numbers, no matter how close together they are, we can always find another rational number between them. And the idea is, if you think about our whole numbers, we found the rational numbers basically by cutting our number line into pieces. And so we can always make a cut between two things, and that cut would be the rational number between them. So maybe we're given two rational numbers and we want to find a rational number between them. There's a pretty cool shortcut that we can use. Basically, you create a new fraction by adding the denominators together and adding the numerators together. And the fraction in the center will be a rational number that's greater than the smaller and less than the larger. So if we have 7 over 18 and 1/2, first we would need to figure out which one of these is bigger. So 1/2 and 7 over 18. Well, let's think about 7 over 18. If it were 9 over 18, that would be equal to 1/2. And since we have fewer than 9 pieces to consider, we can be confident that 7 over 18 is less than 1/2. Then the rational number between them would be 7 plus 1 for the numerator, 18 plus 2 for the denominator, in other words, 8 over 20. Then we could simplify that if we want to, but technically this rational number, 8 over 20, is between the two fractions that we were given. And let's take a look at one more example that's given in the book, and it's talking about the sequence 1/2, 2/3, 3/4, 4/5, and so on. And hopefully you can see a pattern here that the denominator of one term becomes the numerator of the next term. And then the pattern just continues where the denominator is growing by 1, and then it's passing on to the next term's numerator. So essentially we're saying that a term can follow the pattern n over n plus 1, and then the next term would add 1 to the numerator, and it would also add 1 to the denominator. And we want to show that this is an increasing sequence, meaning that the next term is larger than the previous term. And we've showed how to do this. We just need to multiply through by our denominators. First, let's simplify the rational number on the right side. So we have n plus 1 over n plus 2, and we want to show that that's larger than n over n plus 1. So we'll multiply through by our denominators on both sides of our inequality. Remember that the denominators divide off, one on each side. So on the left, we actually have n times n plus 2, and we're trying to show that that's less than n plus 1 times n plus 1. We'll distribute on both sides. We'll have n squared plus 2n. We want to show that that's smaller than n squared plus 2n plus 1 squared. And we can see that n squared plus 2n matches on both sides, but on the side that we're claiming that's bigger, there's a plus 1 squared. So that in itself shows us that the right side is larger. If we wanted to, we could simplify by subtracting n squared and subtracting 2n from both sides. That would remove the n squared terms and the 2n terms. So we'd have 0 on the left and 1 on the right, which is true, which means our original assumption, it was true as well.